Hello, everyone. For today's lecture, we will be learning about chemical reactions. Chemical reactions are chemical changes in which one or more substances are destroyed and one or more new substances are created. Below, we're showing a visual representation of the formation of water from two diatomic atoms, molecules of hydrogen, and one diatomic molecule of oxygen. And you can see here that in the reactant side, which is on the left, we have hydrogen and oxygen that exists as a gas. And through a chemical change, we now form two water molecules that exist as a liquid. So let's dive into what a chemical reaction is, the different types of chemical reactions, and the type of information that chemical reactions tell us. So first we'll break down the parts of a chemical reaction. There's going to be two sides, reactants, which are on the left, and products, which are on the right, that are separated by the arrow. Reactants are substances that are destroyed by the chemical changes, and this is breaking bonds. And they're the same bonds that we talked about in our last lecture. The products are substances that are created by the chemical change, and this is made through the formation of new bonds. And the arrow is read as yields. So we would say that the reactants have their bonds broken and then yields the formation of these products. There are other symbols that you might see in chemical reactions, such as symbols for solids, liquids, and gas. This tells us about the states that the compounds exist in. So on the first slide, we saw that we started out with hydrogen and oxygen gas, and the product of that chemical reaction is water that exists as a liquid. There's also a Q symbol, which means an aqueous solution, and these are when the substances are dissolved in water. Then we also have the plus, which separates two or more reactants or products, and then again, the yield sign that separates the reactants from the products. These are important symbols that you should know. So while we will be diving into more of the molecular characteristics of chemical reactions, and we won't be able to see those bonds breaking or being created, there are some different signs that we can look at visually with our eyes that show the evidence of a chemical reaction. The first is the evolution of light or heat. The second is that sometimes we might have a temperature change, and we'll talk about why this happens in a few slides. And so the temperature can either change in an increase or decrease in comparison to the surroundings, and we could measure this using a thermometer. Another evidence of chemical reaction is the formation of gas. So you can add two reactants together, and the products that they form can also be a gas or sometimes an odor. So you can either visually see maybe some steam coming, or you might be able to smell that as well. Another evidence of chemical reaction is a color change, and an example of this is rust, and this is due to the formation of a new substance that we can visually see. We can also see the formation of precipitate, which is a new solid that's formed from the reaction of two aqueous solutions. So remember, aqueous solutions are when we have compounds that are dissolved in water, and sometimes you might add two compounds that are dissolved in water together, and you can actually see a precipitate. And in this example, the precipitate is this yellow cloud that you can see that actually separates from the water. So we talked about how temperature changes can be a sign of a chemical reaction. And there are two types of reactions that we kind of want to think about. So the first we're going to talk about is exothermic reactions. And this is a chemical reaction if energy is given off by the system to the surroundings. So The system is going to be our chemical reaction, and the surroundings is going to be where that reaction takes place in. The chemical reaction formula for exothermic reactions have the reactants on the right side that yield a product as well as energy release. The temperature of the surroundings, including the temperature probe, increases during exothermic reactions because the system releases energy. And we won't get into this graph, but you can see that this happens when the energy of the reactants is higher than the energy of the products. So here we're showing this graph. This is the potential energy, and this is the reacting progress. And because you have the reactants that have a higher energy than the products, you're going to release this difference or delta H that is in the middle. And this is what it looks like to have an exothermic reaction. The majority of chemical reactions are exothermic because nature favors a low chemical potential energy. So this is the desired product energy of a product, which is lower than that of the reaction. So naturally in nature, we want to have the reactants yield products that also release energy. Another type of reaction is an endothermic reaction. A chemical reaction is endothermic if energy is absorbed by the system from the surroundings. So this is the reverse. This means that instead of the system giving energy to the surroundings, that the surroundings are going to give energy into the system. And the chemical reaction for endothermic reaction shows reactants plus energy on the left side, and then products on the right. So in this chemical potential energy plot versus reactant products, again, we can see that the reactants, this is swapped. So the reactants have a lower energy than the products. That means in order to form the product, we actually have to put some energy in. So the arrow is going up. The temperature of the surroundings, including the temperature probe, decreases during endothermic reactions because the system absorbs energy. Endothermic chemical reactions are generally unfavorable, but may occur only if they are accompanied by an increase in entropy or disorder of the system. Due to more particles formed, liquids or gas formed, mixtures are formed, volumes or gas are formed. But essentially the takeaway from this slide is that you have to actually put in energy in some way on your reactant side in order to make the products happen. And so while this isn't favored by nature, a lot of chemical reactions that we see, a lot of the things that we do in our lives actually take energy and put in their endothermic reactions. And to circle back to what we talked about with either a change in temperature being a signifier of a chemical reaction that's occurred, and exothermic reactions, these reactions oftentimes give off heat because we are releasing energy to this system, to the surroundings. And then in endothermic reactions, this can be signified by the actual surroundings becoming cold because the heat is being taken from the surroundings and going into the system. So there are five basic types of chemical reactions that you will need to know. A single replacement, a double replacement, a synthesis reaction, decomposition, and combustion. So let's go into all five. For a single replacement reaction, a single uncombined element replaces another element and an ionic compound. There are two reactants and two products. So here we see that we have zinc and copper sulfate on the reactant side. And then we form the product of zinc sulfate and copper. And I hope what you can appreciate is that what we did was swap this sulfate group from the copper to the zinc. And that is a single replacement. We replaced one of these compounds with another. So that's kind of shown here in this little cartoon where you have this person here in the orange plus this couple, and the one of the partners in this couple is now going to be with the person in the orange here, and they're dancing. and this one person is by themselves. So just think that you're making one replacement here. Now we also have something that's called a double replacement reaction. Parts of two aqueous ionic compounds switch places to form two new compounds. There are two reactants and two products. So what you can see here is that you have this like singular metal and then this compound here, and it's going to swap to form this compound in this singular metal. But here in this example, you have two reactants and two products. So we have silver nitrate plus sodium chloride. And what you're going to just do is swap these polyatomic molecules here on this side and this non-metal here in the ionic compound to form silver chloride and sodium nitrate. So we just swapped them. And again, in this example, this cartoon here, you can see that we have these two individuals. One has a black hat and one has a white hat on. And then what they do is they just swap their hats, or at this point, we just swap our non-metals, we replace them. So now the individual that had the black hat now has the white, and the individual that had the white hat now has the black. For the third reaction is a synthesis reaction. This occurs when two or more simple substances, the reactants, combine to form a new complex substance, the product. So we are going to synthesize a new product. Here we have magnesium and oxygen, and we're going to form magnesium oxide. And this again is shown here in this cartoon where you have this bird-like creature and this worm, and they're going to come together and they're going to form this completely different type of creature here. So there's some different types of synthesis reactions where you can have an element A and plus element B, and you can make compound here. So this is sodium chloride. Then you can have element plus a compound. So here we're just distinguishing that you can have like a single element and form a compound. Then you can have an element plus this compound. So the compound has two elements put together and you can form compound B. And then you can also have types of synthesis reactions where you have compound A and compound B to form compound C. So here you just really want to focus on, is it an element and the elements are just right off of the periodic table? Is it an element and a compound? Or are there two compounds coming together? Either combination results in a synthesis reaction or the formation of a new product. The opposite of synthesis is a decomposition reaction. This is a more complex substance, the reactant, that is broken down into two or more simple parts or products. Again, synthesis and decomposition reactions are opposite. So here we have water molecule, and it's going to be decomposed or broken down into hydrogen and oxygen. So in our cartoon, we see that we have this egg, and the egg is going to break down into an egg and then your turtle. And this is going to be called the electrolysis of water. And this is very important because we are going to use the hydrolysis or electrolysis of water later on in some of our biochemical reactions later on in the course. The fifth reaction that we're going to talk about and that we need to know are combustion reactions. All combustion reactions involve oxygen as a reactant combining with another substance. All combustion reactions are exothermic. Again, so that means that the system is going to give off energy into its surroundings. Complete combustion of a hydrocarbon always produces carbon dioxide and water. An incomplete combustion of a hydrocarbon will produce carbon monoxide, and possibly carbon, which is black soot. So when you have this complete combustion, you're actually going to form fire or flame. And here are some examples here where you have methane, which is a gas, and then you'll have oxygen, and this forms carbon dioxide and water. So this is complete combustion. This is going to give us our blue flame. Then you might have methane plus um, 1.5, and we'll talk about what these means a little bit later, but this is an incomplete combustion because we only form carbon monoxide and water. This is going to give us a yellow flame. And then here you have methane and um, oxygen. We're going to form carbon, so we're losing that oxygen. And this will make sense when we talk about balancing equations, but this reaction also results in an incomplete combustion, which gives us yellow flame and soot. So if you've ever started a fire and you see the different types of the flame, like the blue part and the yellow flame, this is what's happening. And a good thing that you should take away from this slide is that your combustion reactions have oxygen in the reactants. They are exothermic, so they give off heat. And then you can identify a combustion reaction by the products being carbon dioxide and water. So we're going to talk about some special reactions that happen particularly with metals. They're called oxidation and reduction reactions, or redox. Redox reactions are a special reaction where electrons are exchanged. These are the reactions that result in ionic compounds. So oxidation is going to be the loss of electrons, or oil. So oxidation is loss, or reduction means that we have a gain of our electrons. So oxidation and reduction always happen together. One cannot gain electrons until the other gives them away. So here we have this reaction where we have zinc and copper, and the copper has this +2, and we learned about charges. And this is a redox reaction because this zinc is going to gain the 2, is going to have a +2 charge, and then we're going to have copper. And so we're actually going to look at these reactions separately. We're going to look at what we call half reactions. And so what's happening here to the zinc, we're going to isolate. We're going to have zinc yields this zinc +2. And in our last slide, we talked about when you have a plus charge, that actually means that you have lost electrons, right? So you have more protons now than you mean electrons. And that means that our electrons are going to be on our product side. And then when we just isolate the copper reaction, we see that we go from this copper +2, and it's going to gain the electrons. So it's going to gain these electrons that the zinc lost to become copper. And so because it had a +2 charge, meaning it had 2 more protons than it did electrons, and now we just gave it 2 electrons back, this copper is going to be neutral. So we have certain oxidizing and reducing reagents. Oxidizing agents causes another species to be oxidized. And again, oxidize means loss of electrons, and that's what happened here in this reaction. And therefore itself is reduced, or it gains electrons. And then, so copper in that reaction is our oxidizing agent, and then our reducing agent causes another species to be reduced, and it itself is oxidized. And so reduce means that it gains electrons, and so the zinc caused the copper to be reduced or gain electrons here in this reaction. And they have to happen together. So you can't have oxidation without the other. So these are just some types of reactions here. Let's go more into these redox reactions. And so here we have iron plus oxygen that are going to come together, and they're going to form this iron oxide compound here, or ionic compound. And even though these don't have charges on them, this is indeed a redox reaction. So on the reactant side, we see that both of these are in their elemental state. They have no charge. But in this ionic compound, the iron has a +3 charge and the oxygen has a 2 minus charge, meaning that the iron lost electrons and the oxygen gained electrons. So this indeed is a redox reaction. So let's write these half reactions here. When we write half reactions, we're going to kind of ignore the oxygen here. So we have the iron is going to lose electrons, which is going to be oxidized, right? So we lost 3 electrons. They're on the product side. That's how you know that you've lost them, because they're on the product side. And so here we see iron loses electrons, so it's oxidized. And it's oxidized by oxygen, right? So since it's oxidized, that means that the oxygen has to be reduced. So on this part of the reaction, we see that the oxygen has now gained, so 4 electrons, and now it has this 2 minus charge. And we will talk about coming up what these coefficients mean. That's why it's 4 electrons and not 2, because you have this coefficient here. So how about you pause the video and you can try with this zinc and magnesium oxide example. And we will discuss this. We'll go over this example in class, but pause the video, take some time and see what you come up with. So now we're going to talk about the conservation of mass. During a chemical reaction, atoms are neither created nor destroyed. This means this is the law of the conservation of mass. And so in this example, we have hydrogen and oxygen. They're gases and they will react to form water. But this reaction is not balanced. We don't have a conservation of mass. We can see that here we have 2 hydrogen and 2 hydrogen, but we have 2 oxygen and 1 oxygen here, which means that we randomly lost an oxygen, and that cannot be a thing. So let's dive more into that. So what's wrong with the equation above is that this oxygen went missing. And according to the conservation of mass, the proper way to write this reaction is to put some coefficients in front. So a proper, or what we will describe as a balanced reaction, will have 2 hydrogen, diatomic hydrogen molecules, 1 diatomic oxygen molecule that will form 2 hydrogen, 2 water molecules that exist as a liquid. And the red coefficients represent the number of molecules, and we'll discuss the number of moles of each reactant or product. And so we're going to understand in the next couple of slides why these coefficients now mean that we have a conservation of mass in this reaction. So to count the atoms properly, we need to understand subscripts and coefficients. And we talked about subscripts or superscripts when we were doing our ionic compounds. And so subscripts are at the bottom and they tell us how much of each atom is in this compound. So in this reaction, we have 2 oxygens. Coefficients tell us how many of that molecule that we have. So the coefficients go in front of the molecule, and these coefficients must be divided by the subscript. So here, since we have a 2 in front of water, we see that there's actually 4 hydrogen. 2 times 2 is 4. And then you also multiply that by the oxygen as well. So we have 2 oxygen as well. And you can see now that this reaction is balanced because we have 2 oxygen and 2 oxygen here, and we have 4 hydrogen and 4 hydrogen here. So we are going to discuss how to balance reactions. When we react compounds, we must recognize that all the matter we have at the beginning of a reaction must be present after the reaction. The matter may be rearranged, but we must account for it all. Balancing chemical reactions requires that we have the same number and type of atoms as reactants that we have as products. So these are ball and stick models of hydrogen and oxygen, which can help visualize better what we mean when we say we have to have the same amount of atoms on both sides. So we have 4 hydrogen molecules here, and we have that coefficient, and we multiply it by the subscript, which gives us 4. We have 2 oxygen molecules. So this little subscript here means we have 2 here. And in order to conserve the mass, we have enough hydrogen and oxygen on the reactant side to make 2 water molecules. So now we have 4 hydrogen, so the coefficient multiplied by the subscript is 4, and we see 1, 2, 3, 4, and now we have 2 oxygen molecules. 1, 2. And our reaction is balanced because we have the same amount on the product side that we do on the reactant side for each atom. So how do we balance chemical reactions? We must remember that the number and type of atoms on each side must stay the same. What do the 2's in front of the formulas mean? In order to get the same number of atoms of each type on both sides, we need to add atoms. These numbers, again, are referred to as coefficients. We change these to balance the reactions. So this is important because, for example, you might get a question that gives you an equation that is not balanced, and you might be asked to balance. You cannot change subscripts. However, you can add coefficients. So you can add these big numbers here, but you cannot change these numbers because these numbers dictate what the compound is actually made of. So in the equation above, it reads that we have 2 atoms of sodium, 2 atoms of sodium with 2 molecules of water, 2 water to produce 2 formula units of sodium hydroxide. It's ionic, so we refer to these as formulas. So 2 formulas of sodium hydroxide and 1 molecule of hydrogen. And this doesn't have it has 1. We don't write 1 as the coefficient. So this is how you would read this reaction. So the requirements for a balanced chemical equation is correct chemical formulas must be used for all reactants and products. We cannot change these in the process of balancing. That means we can't change the subscripts. The formulas have to stay the same. The number of atoms of each element in the reactants must equal the number of atoms of each element in the products. Any charge on the reactant side must equal any charge on the product side. So that's where our redox, oxidation, and reduction reactions come in, because we can't have a charge on the products that didn't exist in the reactants. Only the smallest whole number coefficients are acceptable, and that means that you might have to divide a number to get the smallest coefficient. You just don't want to keep adding up and up and up. So you want to make it the smallest whole number coefficient. We'll do some examples in the following slides, and you will satisfy all this by adjusting the coefficients. So, steps for balancing. Find the atom you have the most of. Leave hydrogen, oxygen, and polyatomic ions until later. Balance that atom by adjusting coefficients. Then you balance polyatomic ions as a unit if they appear on both sides of the reaction. If they don't appear on both sides, you will need to balance each element separately. Balance hydrogen and oxygen last. If either exists as a diatomic, leave it for the very last. Check to see that all atoms are balanced with the smallest whole number coefficient, and then you're finished. Let's do an example. So we have potassium nitrate, and that is going to decompose to form potassium nitrate and diatomic oxygen. So let's start by counting atoms on each side. So how I like to set up these equations is that you have the atoms here in the middle. So we have our potassium, our nitrogen, and our oxygen that are in the equation. And then we have the numbers that are on their reactant side to the left, and then the number that is on the product side to the right. So on the reactant side, we have one potassium, we have one nitrogen, and we have three oxygen. And that's indicated here by the three. That is the formula of this molecule. On the product side, we have one potassium, we have one nitrogen, and we have four oxygen. So we see here that the oxygens are not balanced. We have somehow gained an oxygen molecule that we did not have in the reactant side, so we need to balance the equation. So we need to add a coefficient somewhere so that we can have more oxygen on the reactant side than we do on the product side. So let's add a 2 coefficient in front of this molecule, and then we're going to count again. So now that we've added a 2, we have 2 potassium because we're going to multiply the coefficient by each atom. So we have 2 potassium, we have 2 nitrogen, and now we need to multiply the coefficient by the subscript. 2 times 3 is 6. So we have 6 oxygen now on the product side. And if we look on the reactant side, I apologize. And now let's look at the product side. We have 1 potassium, 1 nitrogen, and 4 oxygen. So now we have more oxygen on the reactant side than we do on the product. It's still not balanced. We're almost there. So now we see, again, not only that we have more oxygen on the reactant side, but now we also have more potassium and nitrogen on the reactant side as well. So one thing that we are going to do is add a coefficient to balance the potassium and nitrogen. And we're going to start with the potassium and nitrogen first because in our rules, we said that we're going to leave the oxygen to last. So let's add a 2 in front of this molecule that we formed on the right side. So if we put a 2 and count again, we have 2 potassium, we have 2 nitrogen, and now we have 2 times 2 is 4 oxygen. But let's not forget that we also have these 2 oxygen here, 4 oxygen plus the 2 that are in this diatomic oxygen equals 6. And now that we have a balanced equation because we have 2 potassium on the reactants and 2 on the products, 2 nitrogen on the reactants and the products, and then 6 oxygen on the reactants and products. Everything is balanced. So now we're going to try this molecule here. So let's count up our atoms. In this example, we are going to try to balance the following equation. We have calcium oxide plus phosphoric acid. That's going to lead to calcium phosphate and water. So for this example, because we have a polyatomic atom that exists on our polyatomic molecule that exists on both the reactant and the product side, we're going to count these as 1. So let's have our atoms in the middle, calcium, phosphate, hydrogen, and oxygen. And if we count on the reactant side, we have 1 calcium, 1 phosphate, 3 hydrogen, and 1 oxygen. And on the product side, we have 3 calcium, 2 phosphates, 2 hydrogen, and 1 oxygen. And you can see here that besides the oxygen, most of these are not balanced. So according to our rules, we're going to do polyatomics second to balance, and then we're going to save the hydrogen and the oxygen for last. So let's balance the calcium first. We see that we have 3 calcium on the product side. So let's add a 3 coefficient here and add up all of our molecules on the reactant side. So now we have 3 calcium, so that looks balanced. And we have 1 phosphate, we have 3 hydrogen, and 3 oxygen. So now our calcium is balanced. However, our phosphate is not, and neither is our hydrogen or oxygen. So now we're going to try to balance our phosphate. So we see that we have 2 phosphate molecules here because of this subscript. So let's put a 2. And when we do it, we have to put it in front of this entire compound here, this phosphoric acid. So if we add a 2, we have to multiply the 2 by 3, which is 6 for the hydrogen. We have this whole entire thing we count as 1. So we have 2 phosphates. And now we can see that our phosphates are balanced, but our hydrogen and our oxygen are still not balanced. So now we're going to balance the hydrogen and the oxygen. And I do want to note that we're not balancing the O that's in the phosphate because we are counting this as one entire unit. So you don't want to count that there. So we have 3 oxygen that are on our reactant side. So we're going to put a 3 where the oxygen is, and we're going to put it in front of this water molecule. So when we put the 3 in front of the water molecule, we see that we have now a balanced equation where we have 3 calcium, 2 phosphate molecules here. Again, we can denote that by putting these parentheses around. Then we have 6 hydrogen because 3 times 2 is 6. And then we have 3 oxygen because the 3 coefficient times the 1 oxygen here is 3, and we're all done. So now that we've learned how to balance reactions, what exactly does this tell us? We have been looking at the balance reaction in terms of the number of atoms on each side. We can extend that thinking to the number of molecules on each side. This can also extend to the macroscopic world where we talk in terms of the number of moles of each reactant and product. So we are going to introduce a new concept called the mole. And 1 mole is 6.022 times 10 to the 23 molecules or atoms. So this is a very large number, as we learned in our scientific notation, and that's because atoms and molecules are very, very small. So 1 mole is 6.022 times 10 to the 23. And this number is a way similar to like a dozen. So we know that 1 dozen of anything is 12 objects. So a dozen of donuts is 12 donuts. So let's do an activity that explains the mole. So we're going to be converting between moles and molecules. And what we're going to do is use some kind of dimensional analysis to try to understand how we convert between moles and atoms. So let's say, for an example, you get a question that tells you you have 3.24 moles of iron. Well, we want to know how many atoms are there. So we're going to set up this reaction, this conversion factor. So we know that 6.023 times 10 to the 23 atoms equals 1 mole. And because we have mole on the top and mole on the bottom, we can cross these out and multiply 3.24 moles by 6.023 times 10 to the 23 atoms. And what this is telling us is that in this amount of iron, so 3.24 moles of iron, we actually have 1.95 times 10 to the 24 atoms of iron in that volume. And you can also do the opposite. You can go from particles to moles. So if someone tells you you have 9.54 atoms of iron, now we have to flip that, that equation. So we have 1 mole is 6.02 times 10 to the 23 atoms. And because atoms is on the top and the bottom, and we just divide now 9.56 because it's on the top by 6.023, that's times 10 to the 23 atoms. We now have 1.59 times 10 to the negative 23 moles. So the mole represents for us, again, the 6.022 times 10 to the 23 atoms or molecules or formula units. And how does this relate to the average atomic mass we find on the periodic table? So if you remember from our periodic table, we will have a symbol for each element, and then we will have an atomic number that tells us the amount of protons and the amount of electrons that that atom has. And then we will also see that we have an atomic mass. So if I have 1 atom of carbon, the average atomic mass is 12.01 atomic mass units. And again, that can be found on the periodic table. So let's say we now have 1 mole of carbon atoms. The mass of that mole of carbon would be 12.01 atomic mass units times the 6.022 times 10 to the 23, and that would equals 7.23 times 10 to the 24 atomic mass units. And so now remember, the atomic mass units actually can be equated to grams. So we're going to take this now from atomic mass units, and we're going to try to work in grams. So we take this answer that we get, 7.23 times 10 to the 24 atomic mass units, and we multiply it by what we know 1 atomic mass units to be. And this is from our first lecture where we talked about how small the atom is, that we needed to come up with its own measurement, but 1 atomic mass unit is 1.66 times 10 to the negative 24 grams. And because we have atomic mass units here and atomic mass units down at the bottom, these cross out, we left in grams, and we get the same number that is on the periodic table, which is 12.01 grams for carbon. So what can we conclude? The mass of 1 atom and atomic mass unit is the same as 1 mole in grams. This number is also referred to as Avogadro's number because it was Avogadro who determined the number that would give you the same mass as 1 atom, but in the units of gram. So all this is telling us is that we can say 1 mole of an atom is equal to that atomic mass, 12.01 grams. It's on the periodic table. So we come up with a new conversion factor, which is that 1 mole equals whatever this atomic mass, this gram is, for that molecule, for that atom. So this is for an element, but we are going to be working with compounds. So now let's understand how we can assign a mass to a compound. For ionic compounds, we're going to talk about formula weight. Formula weight is exactly the same as molecular weight, which we will see on the next slide. We simply use a different name because the atoms are ions and they are ionically bonded. So when we have ionic compounds, we refer to them as formulas. When we have covalent compounds, we refer to them as molecular weight. So let's take zinc bromide. For this formula here, we have 1 zinc and 2 bromine atoms. So if we look on the periodic table, we see that the atomic mass of zinc is 65.4 times 1. So we have 65.4 mass. And then for bromine, we have 2 on the periodic table. Bromine's atomic mass is 79.9. And we have 2 of those, so we have to multiply it by 2. And that is 159.8. To understand the weight of this zinc bromide, we add the two of these together to get 22.5. And so for one formula unit of zinc bromide, we can either have 22.5 225.2 atomic mass units. But then again, remember, due to Avogadro's number, we know that 1 mole of zinc bromide is the same in grams as the atomic mass unit. So what we're going to talk about is the molar mass, and it is written as 225.2 grams per mole. And that's because of this equation here. When we have a molecule, we determine the mass of a mole by determining the molecular weight. The molecular weight is the sum of the masses of the individual atoms in the molecule. So here we have this C2H6 oxygen molecule. And similar to what we did on the last slide, we're going to take these weights that we get from the periodic table for each of these atoms and multiply them by the subscripts that we see here. So in this compound, we have 2 molecules of carbon, we have 6 molecules of hydrogen, and we have 1 molecule of oxygen. And when you multiply how many by their atomic weights from the periodic table, you get 24 grams for carbon, 6 for hydrogen, and 16 that equal 46.068. And so 1 molecule is 46.07 atomic mass unit, but we can also read this as 1 mole of C2H6O is 46.07 grams. And this molecular weight is again what we call the molar mass, and it is written as 46.07 grams per mole. So what you should understand from this section is that you should be able to look at a compound or a formula. You should be able to look at the individual atoms on the periodic table and come up with some type of formula or molecular weight, and then write it as a molar mass, which is going to be the grams that you calculated divided by a mole. Now, sometimes it's important for us to know what percentage a particular element contributes to the overall mass. So what we do here is calculate a mass percent composition. And all of this is just to help us understand what kind of materials that we're dealing with in chemical reactions. So your mass composition is going to be the mass of the element in the compound divided by the total mass of that compound times 100. So for example, in this C6H6 molecule, we have 6 carbons that equal 72.06. We have 6 oxygen that equals 6.048 for a combined molecular mass of 78.108 or 78.11. If we want to know how much of that mass is due to carbon, we take 72.06 and divide it by the total, which is 78.11 times 100, which is 92.3%. And if we want to understand how much of the mass is contributed by hydrogen, we take its contribution or amount in that compound, divide it by the total, and multiply by 100, and we get 7.7. And what this is telling us is that the bulk of this compound, the mass is contributed to by carbon and not hydrogen. So now we're going to look at the equation below and kind of put everything together that we learned. In this chemical reaction, we have the amount of reactants, and we have on the left side, it yields these 2 products. And we learn that we can have a formula weight that is equal to 1 mole. So if you were to add up all the atoms in this molecule, you get 159.7 grams. For this reaction, you see you have this coefficient here. So we have 3 molecules of carbon monoxide here, and that gives us an 84.0 grams. So we have 3 moles at 84.0 grams. We yield a product of 2 iron molecules. So we have 2 atoms of iron. We can also say we have 2 moles. So the coefficients tell us how many moles are here, and that gives us 11.7 grams. And then for this moles of carbon dioxide, we have 3 molecules of carbon dioxide, or also 3 moles of carbon dioxide, with a molecular weight, um, with a molar mass of 132 grams. And if you can add up these values, you will notice that the mass of the reactants add up to the same number as the mass of the products. And that is our conservation of mass. It has to be conserved. So we can convert between moles and mass by using a gram per mole conversion factor. So we have the moles of a substance. We can convert to the mass of a substance, having the grams on the top of our equation with moles on the bottom. And then if we want to do the reverse, by converting from the mass of our substance to the moles of our substance, we'll have the moles on the top divided by the gram. Remember, the molar mass is the mass of 1 mole of a substance, and the units of a molar mass are grams per mole. So molar mass conversion factors are written from molar mass. They relate grams and moles of an element or a compound. So if we were to write a molar mass factor for methane, which is CH4, used in gas and stoves, we know that the molar mass is 1 mole of methane equals 16.0 grams. And we know that from the molecular mass because we've taken the 12.01 from the carbon, the 1.01 from hydrogen times 4 molecules, that equals 16.0 grams. And this is how we're going to write this conversion factor. We're going to write 16.0 grams of methane over 1 mole of methane. And we can also write it on the reverse. So remember, depending on what we want to do, whether we want to know the moles or the mass, that's going to determine whether the mole is going to be on the top of our fraction or on the bottom of our fraction. So we can also express 1 mole as 16.0 grams. So these are our conversion factors expressed as molar mass. So let's do some problems using molar mass to convert from mass to moles. So you might get a question that says, how many moles of helium are in 40 grams of helium? So we look at the periodic table and we see that helium has a molar mass of 4 grams per mole. So what you can do is take that number, the atomic mass that's on the periodic table, and instead of having AMU, you're going to put 4 grams per mole. So let's set up our equation. We take what we are given, which is 40 grams of helium, and because we want to go from mass to moles, so again, we want to go from mass to moles, we want to have our moles on the top and our grams on the bottom. So we have 1 mole on the top. We're going to take this molar mass here and have grams on the bottom, and you're going to multiply over the top. So 40 times 1 is 40. And then you're going to divide by the number on the bottom, which is 4. 40 divided by 4 is 10. And so the answer to this question is that there's 10 moles of helium and 40 grams of helium. How about a molecule that has more than 1 atom? How many moles of carbon sulfide are in 3.8 grams? So first, we need the molar mass. So we have 1 carbon here, so 12.01 times 1, and then we have 2 sulfur atoms, 32.07 times 2, so the 2 comes from the subscript, that gives us 64.14. So if we add these together, we get a molar mass of 76.15 grams per mole. So let's set up our equation. We are given that we have 3.8 grams of starting material, 3.8 grams, and now we're going to set up our molar mass conversion. We have 1 mole on the top, and we have 76.15 grams on the bottom. And one thing that you can also say is that what goes up must come down. So what we have up is grams. We have to have grams down at the bottom. So we're going to multiply through the top, 3.8 grams times 1, and then you're going to divide that by 76.15. Our grams are going to cancel out, and so we have 0.050 moles as our answer. So how about we convert from moles to mass? How many grams will 5.00 moles of chlorine weigh? We know that the molar mass from the periodic table is 2, because we have this subscript here, 35.45 grams per mole. This value is found directly on the periodic table, and that equals 70.90 grams per mole. Now we're going to have the flip because we want to have grams on the top and moles on the bottom. Again, our starting material is 5.00 moles of chlorine, and so what goes up must come down. So we want our moles on the bottom. We're going to multiply through the top first. So 5 times 70.90 grams is 355 grams. And we can say there's a 1 at the bottom. So our final answer is 355 grams of chlorine. Now, we converted from moles to mass and mass to moles. But remember, we know how many molecules are in a mole. So let's figure out how many molecules are converting from molecules to mass. So we already saw how to convert between molecules and moles. Now we can extend that to mass. So we can ask the question, how many molecules of carbon sulfide are there in 3.8 grams? So we have 3.8 grams, and we are going to use the same mass, molar mass. So we have our moles at the top and our grams at the bottom. What goes up must come down. If we divide 3.8 grams by 76.15 grams, we get 0.050 moles. But we also have a conversion factor from molecules to moles. So let's see what that looks like. We're going to take this number here, this 0.050 moles, and we're going to multiply it by the fact that we have 6.022 times 10 to the 23 molecules in 1 mole. Again, what goes up must come down. So if we multiply 0.050 by 6.022 times 10 to the 23 molecules, we get 3.0 times 10 to the 22 molecules. So this is a way that we can understand how many molecules and mass we have in a mole. So here is a diagram that can help guide you on how to set up some of these equations. So if we're starting out with mass and we want to understand moles, we're going to divide by the molar mass. If we have moles and we want to get back to mass, we're going to multiply by the molar mass. If we have moles and we want to get to how many particles or atoms that are in a mole, we're going to multiply by 6.02 times 10 to the 23, which is Avogadro's number. And if we have particles and we want to get to moles, we're going to divide. So let's put together the information we know about balanced chemical equations with the mole. Our balanced chemical equation gives us coefficients which tell us how many moles of each reactant and product are involved in the reaction. Let's use those coefficients to convert from moles of one species to moles of another. This relationship is known as the mole-to-mole ratio. So we're going to talk about stoichiometry. Chemists use stoichiometric calculations to predict the amount of reactants used and products formed in specific reactions. The first step in solving stoichiometric problems is writing the balanced chemical equation, which we learned how to do. Now we're going to use mole ratios derived from the balanced chemical equation to set up our stoichiometric calculations. Stoichiometric problems make use of mole ratios to convert between mass and moles. So how do we identify the mole-to-mole ratio? What we do in our chemical equations here, so we're taking nitrogen gas plus oxygen gas and forming nitrogen oxide. Our nitrogen dioxide here. I apologize. So we're going to look at the coefficients, which are the numbers in front of these molecules, in order to determine how many moles are there. So you will need to know that these coefficients equal how many moles. In this equation, we know that there's 1 mole of nitrogen gas, 2 moles of oxygen gas, and 2 moles of nitrogen dioxide gas. So if we want to say the mole to mole ratio between nitrogen and its product, nitrogen dioxide, then we know we can just take these coefficients and write them as a ratio. So we have 1 mole of nitrogen gas to 2 moles of nitrogen dioxide. And we can write the mole to mole ratios as such. So the ratios are written as a fraction, where we have 1 mole of nitrogen gas to 2 moles of nitrogen dioxide. And we can do that in the reverse too, depending on how we need to use the equation, which we'll see in a few slides, that we can flip the equation or the fraction and have 2 moles of nitrogen dioxide to 1 mole of nitrogen. And essentially what this is telling us is that in order to make this nitrogen dioxide gas, we need 1 mole of nitrogen here. So as an example, we're going to calculate the number of moles of sodium oxide that will be produced when 5 moles of sodium completely react with oxygen gas. So we are going to use our coefficients to come up with some mole to mole ratios. First, we're going to start with what we're given. We are given that we have 5.00 moles of sodium. Then we're going to look at our balanced chemical equation to set up a mole to mole ratio. So we know that we make 2 moles of sodium oxide. We're going to write 2 moles at the top. That comes from this equation. And we're going to look at the coefficient in front of sodium. So we have 4 moles of sodium. And this is our mole to mole ratio. And one way that you can know what to put at the top is to see what you are asked. So the question is asking you for the number of moles of this sodium oxide. So you're going to want to end with sodium oxide here. So when we set up this equation with our mole to mole ratio, which is here, 2 moles of sodium oxide to 4 moles of sodium, we multiply by the top, which is 5 times 2, which is 10, and then we're going to divide by 4, and that's going to give us 2.50 moles of sodium oxide. And what this is telling us is that when we have 5 moles of sodium, if this is our starting material, we can make 2.50 moles of sodium oxide. The method of looking at mole relationships in a balanced chemical equation is known as stoichiometry, and we can convert from mass of one substance to moles of another. And this is how we're going to set up this equation. So if you write down this equation and you look at a problem, you can take the information you're giving in the problem to look at the to answer the problem by plugging into this equation. So we start with mass of A, and we want to understand how to get to moles of B, we must go through moles of A using our molar mass and then our mass, a mole to mole ratio. So we will start with the mass of A. We learned about molar mass. So we're going to say we have 1 mole of A to the molar mass of A. Again, what goes up must come down. So we want to have mass at the top and at the bottom. We'll cross these out and we're left with 1 mole of A. Then we're going to use our mole to mole ratio. So we're going to have the mole ratio of B divided by the mole ratio of A. That's going to come from our balanced chemical equation. And so we'll have mole of A on the top. That will cancel out with the mole of A on the bottom. And that gives us our mole of B as our answer. So let's do some mass to mole practice. So if we have 3 molecules of copper sulfate plus 2 molecules of aluminum, that's going to use aluminum sulfate plus 3 moles of copper. So first, I would like to say that this is a single replacement reaction that we discussed earlier. So our question is going to be, how many moles of copper sulfate are required to react with 13.5 grams of aluminum? We're starting out with what we are given. We are given that we have 13.5 grams of aluminum. So we'll set up our equation first with this. Now we're going to use our molar mass that we learned. This will come from the periodic table. We know that 1 mole of aluminum is 26.98 grams. Again, what goes up must come down. So we have grams here. We need to have grams at the bottom, and these grams will cancel out to leave us with 1 mole of aluminum. Now, because we want to know how many moles of copper sulfate we need to react with the aluminum, we're going to use our mole to mole ratio that comes from our balanced chemical equation. The balanced chemical equation tells us that we have 3 moles of copper sulfate, so we'll put that here, to 2 moles of aluminum. So we'll put this here at the bottom. Now we have moles of aluminum at the top that need to cancel out with moles of aluminum at the bottom, and we're left with moles of copper sulfate. So now we'll multiply across the top 13.5 times 3, and then we'll divide that answer by 26.98 times 2, and that gives us 0.751 moles of copper sulfate. So that means that we need this amount of copper sulfate to react with aluminum to make our product. Now, let's do another example. How many moles of aluminum sulfate are produced when 13.5 grams of aluminum reacts? So we're asking how much can we make if we have this amount of starting material? Again, we're going to start with our 13.5 grams of aluminum. We're going to use the same molar mass here. So we have 1 mole of aluminum divided by 26.98 grams. We're going to cross out our grams, and then we're going to have our multiply that by our mole to mole ratio that we get from our balanced chemical equation. We make 1 mole of aluminum sulfate for 2 moles of aluminum here. And so our final answer will have a cross out of aluminum moles and end with aluminum sulfate. And that gives us an answer of 0.250 moles of aluminum sulfate that are produced when we have 13.5 grams in our reaction. We can even extend that to calculating the mass from moles. So we're going to take our stoichiometric equation even further. So we stopped at moles, but we can go to mass. In this question, we're asking how many grams of chlorine would be needed to produce 0.67 moles of CHCl3. Let's map it out. So we're going to go from moles of CHCl3 to moles of Cl2 or chlorine, 2 grams. Let's set up the equation. So our starting material is that we have 0.67 moles. So we're going to start with that. Then we're going to multiply that by our mole to mole ratio. We know from the equation that we have 3 chlorine, so we'll put 3 moles here, and that we produce 1 mole of CHCl3. We're going to multiply that now by our molar mass of chlorine because we want to end in grams of chlorine. So we use this number from the periodic table, our molar mass, which is 70.9 grams of chlorine, to give us which is 1 mole. And we're going to cross out. What goes up must come down. Moles and moles are going to cancel out. Moles of chlorine and mole here are going to cancel out. That leaves us with grams. And when you multiply across the top and divide by the bottom, our final answer is 143 grams of chlorine. So you can take some time and just look at why we need to do this. There's no direct calculation to go from our products to our reactants. And so that's why we first start with our starting material. We calculate the moles. We use the coefficients to find the moles of water and then turn the moles of water to grams. So this is our workflow for how we're going to start with moles of or grams of one product and go to grams of the other. These conversion factors that we learned along the way are going to help us get to that answer. So take some time and do this practice problem. We will go over this in class. And just remember to use your molar mass and your mole to mole ratios. So now we're going to talk about limiting reactants. In the past couple of slides, we used the molar mass and the mole to mole ratio to figure out how much product we can actually make with a certain amount of starting material. So to understand the concept of limiting reactants, we're going to start with the example of making s'mores. Here is the recipe for a s'more. We need 1 graham cracker, 1 chocolate bar, 2 marshmallows. If you have 1,000 graham crackers, 800 chocolate bars, and 1,000 marshmallows, how many s'mores can you make? So if we have 1,000 graham crackers, we could make, in theory, 1,000 s'mores. If we have 800 chocolate bars, we can make 800 s'mores. If we have 1,000 marshmallows, we can make 500 s'mores. And that's because for each s'more, we need 2 marshmallows and we have 1,000. So 1,000 divided by 2 is 500. So because you will run out of marshmallows after you've made 500 s'mores, that is the most that you can make, right? So I can only make as much as the least amount of material that I have. In this problem, you can see that 500 marshmallows is the least. So even if I have 1,000 graham crackers, I can only make 500 s'mores before I run out of marshmallows. And this is what we call our limiting reaction. Reactants. Marshmallows in this equation are a limited reactant. So given we can do something similar to what we did with the s'mores with chemical reactions, because now we know how to understand how to convert from moles and mass of starting material to moles of product. We can now ask, how much do we need of a certain product reactant to make a product? So given the following balanced react equation, calculate the mass of nitrogen dioxide that can be made from 30 grams of nitrogen monoxide or nitrogen oxide and 30 grams of oxygen. Like the s'mores, we need to determine how much we can make from each reactant. So we're going to start by setting up equations like we did in the previous slide for each of our reactants. We are given that we have 30 grams of nitrogen oxide and 30 grams of oxygen. Let's start with NO first. So let's set up our equation just like we did before. We start with grams, and then we're going to use the molar mass to understand how many moles of nitrogen oxide we have. Then we're going to use our mole to mole ratio. So we have 2 moles of the product divided by 2 moles of our reactant. The moles and the moles cancel out, and we're left with 2 moles of our product, nitrogen dioxide. Now we want to know how many grams we can make. So we actually need to use the molar mass for nitrogen dioxide. We do this by calculating the molecular mass, which is 46.0 grams divided by 1 mole. The moles of this nitrogen dioxide are going to cancel out. And if we multiply by the top and divide by the numbers on the bottom, we can say that if we have 30 grams of nitrogen oxide, or nitrogen monoxide, we can make 46.0 grams of nitrogen dioxide. Now, let's look at oxygen. If we start with 30 grams of oxygen, we can use our molar mass to know that we have 1 mole of oxygen is 32 grams. The grams are going to cancel out. Then we'll use our mole to mole ratio to relate the products to the reactant. So again, we have 2 moles of nitrogen dioxide to 1 mole of oxygen. And then the moles of oxygen are going to cancel out. Now we need to figure out how many grams of nitrogen dioxide we can make from 2 moles of nitrogen dioxide. So we're going to use the molar mass here again. 46.0 grams by 1 mole. If we multiply across the top and divide by the bottom, we get 86.3 grams of oxygen dioxide. Now, similar to what we did with the marshmallows, the chocolates, and the graham crackers with the s'mores, we're going to look at what we have the least of. We have the least of nitrogen, monoxide with 46.0 grams, and we have more that we can make with the oxygen. So we have to go with what we have the least of. So nitrogen monoxide is a limiting reactant because once we have made 46.0 grams of nitrogen dioxide, we will run out of our reactant. So this will wrap up our understanding of our chemical reactants, what a balanced chemical equation tells us about the moles that are in that reaction and how it relates to the grams. We looked at how much product we can make from a certain amount of starting material, and we also learned about our limiting reactant. Lastly, we just want to talk about the fact that not all properties are conserved during chemical reactions. So everything that we've been doing has been to show that we have the law of conservation of mass, that matter cannot be created nor destroyed. So we know that mass has to be conserved in a chemical reaction. We know that the types of atoms have to be conserved in a chemical reaction. And we know that the number of each atom has to be conserved. However, properties that are not conserved are the color. So we talked about rust. So the formation, the things that we see that show us that a chemical reaction has occurred. Something that's not conserved are the physical states. So in multiple examples that we looked at, we saw that you could start with hydrogen gas and oxygen gas and make water, which is a liquid. So the physical state is not conserved. The volume is not conserved, so we can lose some volume, and the number of moles of reactants and products are also not conserved. And so importantly, moles are different than the mass. So remember, the moles are those coefficients, and you can change the coefficients, but you can't change the number of atoms that are in those formulas. So one thing that we need to talk about is sometimes reactions are not 100% efficient. And so everything that we've been calculating so far, example, if we say how much water can we make from a certain amount of hydrogen and oxygen, and we come up with a number, that is our theoretical yield. It is the amount we would make if every molecule were reacted. And unfortunately, this is not usually the case. Molecules often don't react because they simply don't come together in the correct orientation and in the vicinity of other molecules in order to react. So we get what is called an actual yield. This is what we actually make. And what we're going to calculate is our percent yield, and that's going to tell us how successful our reaction is. We calculate our percent yield by taking our actual yield, which we could measure, and we divide it by the theoretical yield, which is what we calculate, and we multiply it by 100. So let's do an example. In this reaction, where we have 2 nitrogen monoxide molecules that combine with oxygen to form 2 nitrogen dioxide molecules, we want to know what the percent yield is. We determined that we can make 46.0 grams of nitrogen dioxide. Again, that's because nitrogen monoxide was the limiting reactant. This is all we can make. But let's say we did an experiment where we took some of this nitrogen monoxide, we added some oxygen, and then we measured the amount that we made in the lab. And our actual yield was 35.0 grams. So what we do is we take our actual yield, which is 35.0 grams, we divide it by our theoretical yield, which is what we calculated, 46.0 grams, and we multiply that by 100. That means our percent yield is 76% efficient. So you can take some time and pause the video and calculate a percent yield for nitrogen gas in this equation. And again, most reactions have a low yield because of the conditions needed for a successful reaction. And so we're going to talk about some solution chemistry in our next lecture, and we'll kind of talk about um, why some reactions are low yield. But just know that some of the reasons why we get low yield are due to chemical orientation. Again, we talked about the amount of energy that sometimes needs to go into these reactions. The temperature may not be right for the reactions to be completely successful. And also, we might need a little bit of help or the presence of a catalyst. So, this is what we learned about chemical reactions, why they occur, um, how we can tell through either light or a gas how these things, chemical reactions, occur. We learned about the different types of reactions: single replacement, double replacement, decomposition, synthesis reactions. We talked about how to balance chemical equations, what that chemical balanced chemical equation can tell us, and how to determine how much product we can actually make from a certain amount of reactions. In our next lecture, we will talk about reactions that happen in solution.